All right, so our next problem, number 72, is really kind of a concept-heavy question based on the relationship between capital A and then little f. So it writes here that A is the definite integral of f, which means, you know, concept-wise, that A is the area under this function right here from 0 to x. So if you were to plug something in for x, it would replace the upper bound and it would represent the area. So as this is the function shown in this figure right here, we're looking for lots of things: local min, local max, inflection points, increasing, decreasing, concavity, as well as absolute max. So lots of different concepts. You guys will have a question like this on your test. So we've got, write the number, a of x is equal to this integral right here. Now, this is actually weird to me. They put x's here. You'll almost always see t's here instead of x's because this x is supposed to get subbed in here. So I'm not really sure why they kept the variable all the same. This is the way that you'll normally see it. This is the way you'll see it on my test. So we are looking for local mins and local maxes and increasing, decreasing. Let's start with that first. All of those things come from the first derivative of a function. So if we are looking for the critical points for A, or where A is increasing or decreasing, we want to start with A prime. So A prime is the derivative of this, which means we need to take the derivative of this. So the derivative of the antiderivative just goes back to f, since this is just a plain old x. So this is f of x. So when we are looking to see when A prime is positive, when A prime is negative, when A prime switches signs, that means we're looking at when f switches signs. Okay, so start with our critical points. So we are going to set this equal to 0 to find our critical points. And so those are literally just going to be the x-intercepts of that graph. So we have 0, b, and d. So all of those are our critical points. Anytime that you're looking to identify critical points as maxes or mins, or to find areas of increasing or decreasing, you set up a sign chart. Okay, so we're going to set up a sign chart that represents A prime. And we're going to start it at 0. We'll have B, D, and then this whole thing ends at E, so you want to make sure you don't go past that. So sign chart for A prime. So between 0 and B, this is up above the x-axis, so we'd say this is positive. Between B and D, it's down below the x-axis, and then this is just kind of a little blip right here where it hits the x-axis but then bounces back down, so this is negative. So we can use that to write maxes, mins, increasing, decreasing. Just going to get a better handle on this here. So this right here, B, would be a local max because A prime changes from positive to negative. So we have a local max at x equals B. We have no local mins because there are no places where your first derivative changes from negative back to positive. So no local min. Increasing would be anywhere that the first derivative is positive, so that would be from 0 to b. Decreasing would be negative. You have to make sure, though, to exclude that point D because it's not actually decreasing there. So that would be what we have so far. Then you do the second derivative to answer the inflection points and the concavity. So A double prime of x, the sign of A double prime will tell us the concavity, and then any change in A double prime will tell us about inflection points. So according to this relationship, A double prime would be equal to f prime. So we want to first start by where f prime is equal to 0. So we want to know when the slope of f is equal to 0. So if we look back at the graph, that would be up here at A, because that's kind of a turning point, down here at C, and then right here at D. So those are the kind of maxes and mins, not kind of, they are the maxes and mins of f. So this is where f prime is equal to 0, kind of a horizontal tangent here, here, and here. So A, C, and D. Okay, so now using those points, we can set up a sign chart for A double prime. Okay, so we mark E and 0 at the ends here. So we have A, C, and D. Sorry, that's not really equally spaced. So we want to know now the sign of A double prime, which means we want to know the sign of F prime. So if F prime is positive, that means this graph is increasing. So here's an increase on F, which means that F prime is positive. Here's a decrease on F, which means that F prime is negative. This is an increase followed by a decrease. So f prime would be positive and then negative. So we use these signs to tell the concavity. We use the sign changes to tell the inflection points. So the inflection points would be at x equals a and c and d, because those are all sign changes on the second derivative. The graph would be concave up anywhere the second derivative is positive. So first from 0 to a, and then again from c to d. Concave down would be anywhere the second derivative is negative. So first interval would be from a to c, and then second interval would be from d to e. Last part of the question asked about an absolute max. So for an absolute max, you check the endpoints and the critical points. And this is a little bit tricky because we can't actually come up with the areas, but we can make a guess because you can tell based on looking at the picture, like, oh, this area is way bigger than this area and way bigger than this area over here. So for the absolute max, here's what's happening. We start here. We gather more and more positive area, right, up until this point. So from A to B, we've accumulated a whole lot of positive area. So the area so far, A has a large positive area. Then we lose a little bit of area, but not nearly as much as we gained. So overall, our accumulation is still positive as we go from A to B and then B to D. And then we lose a little bit more, but again, not enough to make up for what we gained here. So B would be the absolute maximum. Again, normally this would be much more formal where you check the endpoints as well as the critical points, but here you just kind of have to guess based on the areas that you can see. All right, 72, lots and lots of concepts. You'll need a couple of those. I won't ask you every single piece of this question because that would be very long, but you'll need to know how to do everything because I'm going to ask you like 2 or 3 of those pieces on the test. 75 is our net change. This is our 5-5 problem. So it gives us this setup right here. On a typical day, a city consumes water at the rate of, remember this is already a rate, tells you the units, thousands of gallons per hour. T is the number of hours past midnight. What's the daily water consumption, so all 24 hours, and then how much water is consumed between 6 and midnight, so the last 6 hours of the day. So our setup for the daily water consumption would look something like this. If you want to know how an amount has changed, you integrate the rate. So the whole day would be from midnight to midnight, 0 hours from midnight, 24 hours since midnight, and then you put the rate in the middle there. So the 100 plus 72t, and then minus 3t squared dt. So I'm going to have instructions on the test that tell you that all integrals have to be done by hand. The only exception will be this problem, the one that you were doing the setup for net change. So net change, you're going to be able to plug it in your calculator, and I have it like bolded, like it'll stick out to you that you're allowed to do that on that part. So remember, your setup on the calculator looks like this. Press the menu key over on the right, option 4 for the calculus menu, option 2 for the numerical integral, and then you're just going to type in exactly what you have written on your paper. So 100 plus 72t minus 3t squared, and that is with respect to t. So we get 9,312, and remember that was in thousands of gallons. So 9,312, so your first answer would be this, because it's in thousands of gallons. Sorry about that fake comma. So that's your first answer. Second one said between 6 and midnight. So 6 p.m. would be 18 hours past midnight, and then the next midnight would be 24 hours. And same exact rate that you're integrating. In this one too, you'll be able to just plug it right into the calculator on the test. All right, so I'm actually just going to copy paste this one right here, highlighting it and then pressing enter. And I'm going to arrow over, there we go, to the 0 and change that to an 18, because other than that, the setup is identical. And we get 1,680. So the actual integral itself is 1,680, but remember, the units were supposed to be in thousands of gallons. All right, so those will be your 2 separate answers for number 75. You guys will have one just like that.